Hello everyone, and welcome back to physics-based animation. In the last video, we learned all about simulating systems of jointed rigid bodies, which allowed us to simulate robotic creatures like this four-legged walker. But we left out one important detail. We never talked about what happens as the walker's feet come in and out of contact with the ground. But have no fear, we'll solve that problem today when we talk about rigid body simulation with contact. Now, fair warning, this lecture uses all the concepts we learned about in Lecture 7, Rigid Body Mechanics. So if that's still a bit shaky, another watch of that video is highly recommended. Here's a very simple scene featuring two rigid bodies, a circle and a bowl-like object. Let's imagine that our circle is falling downward under gravity. Eventually, these two objects will collide, and we're going to have to deal with this collision somehow. Now we've seen this before, and you may recall from our discussions on cloth simulation that collision algorithms in simulation are typically divided into two phases: collision detection and collision response. Collision detection detects collisions between objects, while collision response decides how to alter the motion of the objects to resolve these collisions. So assuming we have a working collision detector, we can use it to detect points at which our two objects are coincident, that the distance between them is zero. And we call these points, somewhat boringly, contact points. Typically, our collision detector will return not only these contact points, but the contact normals as well. Each contact normal is a unit magnitude vector normal to the contact patch at each point. And the contact patch is the tiny squished surface between the objects. Our goal is to use all this information to figure out how these contacts affect the motion of our rigid bodies. When we discussed collision resolution for cloth simulation, we used a relatively straightforward velocity filter approach, wherein we simply removed the component of each per-vertex velocity that was making contacts worse. Why can't we just do the same thing for rigid bodies? The problem is that you can't manipulate the per-vertex velocities of a rigid body in isolation. Rather, they are all connected via the angular and linear velocity of the center of mass. Sadly, this means our previous simple approach is just not applicable anymore. Fortunately, by the end of this video, we will have developed a more advanced analog to that algorithm that will be able to solve our rigid body contact problem. To get us started on that journey, we need to build up a model for our contact problem. And to do that, we'll start by going over three important rules for contact resolution, criteria we would like our contact resolution scheme to satisfy. To simplify things, we can discuss these rules by looking at a single contact point. And perhaps the most obvious rule or condition on our contact resolution scheme is that it should not allow any penetration at our contact point. In other words, the objects should not be allowed to continue moving into each other once a contact is detected. Now, one way to formalize this is using the notion of a signed distance. Given 2 points in space, one on each object, it's pretty easy to compute the distance between them. Distance is a strictly positive quantity. The name signed distance implies that we can have both positive and negative distances. The real question is, how do we choose the sign? Well, we choose our sign to indicate if two objects have passed through each other. In other words, if a point on one object is inside the other. If this is true, as it is here, we assign the distance a negative sign. The signed distance is a useful quantity in a number of graphics applications, and collision resolution is certainly one of them. Now, using this new tool, signed distance functions, we can formalize our no interpenetration rule. Here are our two objects again. At the moment of collision, we know that the contact point on our first object A and the contact point on our second object must be coincident in space. This is the definition of a collision. Consequently, we know that the distance between these 2 points is 0. If something goes wrong and our objects interpenetrate further, then by definition, our signed distance will become negative. This means that in order to ensure no interpenetration, we need the signed distance between the contact point on both objects to always be greater than or equal to 0. And this is our first rule of contact mechanics. In the previous cloth simulation video, we saw that resolving collisions involves altering the velocity of the colliding objects. We can do this by adding forces due to contact to our physical system. What we need to do is more precisely define how these contact forces act. We know that if two objects are in contact, we shouldn't be able to push them further into each other, but we should be able to pull them apart. In other words, contact forces should not stick objects together. Rather, they can only push objects apart. Also remember that our contact forces don't include phenomena like friction, so they shouldn't change the relative sliding velocity of our objects. That means they should only act along the direction of the contact normal. We can denote this notion mathematically by forcing our contact forces to be a scalar multiple of our contact normal. Further, to ensure that our contact forces can only push objects apart, we can enforce that alpha, the contact force magnitude, must always be greater than or equal to 0. And this gives us exactly what we want. This gives us the second of our 3 rules of contact mechanics. Now that we know how to represent contact forces, there's one more important question to answer, and that is, when are we actually allowed to apply contact forces to our system? Obviously, if our objects aren't in contact, we shouldn't apply any contact forces. The question is, how can we add this notion to our mathematical model of contact? We know that if our objects are in contact, then we might need to apply a contact force to prevent further interpenetration. In other words, when our signed distance at the contact point is 0, then our contact force can be turned on, or alpha can be greater than or equal to 0. Otherwise, if the objects are not in contact, the signed distance between our objects will be greater than 0, and our contact force, i.e. alpha, should be 0. This if statement is our final rule of contact mechanics, and taken together with the other 2 rules, gives us a set of conditions called the Signorini conditions. Note that we have a special name for our if statement condition. We call that a complementarity condition. And we typically write this using this orthogonality symbol. Why use this symbol? Well, you should be able to convince yourself that if you have a vector of distances and a vector of alphas that satisfy our if statement, that the dot product of these 2 vectors will be 0. In other words, the vectors will be orthogonal. The notion of complementarity gives us a compact set of constraints that define successful contact resolution. However, we are missing one fairly important piece of the puzzle, and that's dynamics. Remember that the motion of rigid bodies is governed by the Newton-Euler equations. We somehow need to incorporate this into our contact resolution scheme. In order to see how to do that, we will need to look at a slightly more complicated example. And that example is these 2 colliding spheres. As in our initial example, we assume we have a working contact detector, which will find this contact point and compute our contact normal. Note that we are choosing the surface normal that points from rigid body A towards rigid body B. You've probably been asking yourself why I've been writing down 2 contact points, one on object A and one on object B. Let's take a minute to clear that up. Remember that each rigid body in our scene has an associated reference configuration in a center of mass coordinate frame, which is transformed to the current world space position using the rigid body mapping. For contact problems, we deal with many separate rigid bodies, each with their own mapping. When two objects are in contact, it means that each object maps a point in their respective reference space to a common point in the world space. This common point is the contact point. This is why, even though in these examples contact points are single points in the world space, we track them distinctly for each body involved in the collision. Now that we know a bit about the kinematics of a two-body contact problem, let's talk about how contact forces work in this case. Previously, our push-only contact mechanics rule dictated that contact forces act in the positive normal direction at the contact point. However, we can see now that this amounts to only pushing on a single object. In fact, the second object involved in this collision requires that contact forces act in the negative normal direction, but with the same magnitude, alpha. Having alpha be the same for both directions is required to satisfy Newton's third law, which states that every action has an equal and opposite reaction. This just highlights that we have to be very careful about keeping track of which direction the contact normal is pointing in order to apply contact forces correctly. Okay, after all of that, here's the whole picture for our two-body contact problem. We have a set of dynamics equations for each rigid body in the scene, and we have a set of constraints for each contact point. Our continuous dynamics equations, unfortunately, don't really do us any good yet. But that's okay, because we already worked out some appropriate discrete update equations a couple of videos ago. So if we bring those discrete update equations back, we now have all the information we are going to need to build our contact handling algorithm. Now I realize this looks like a lot, but now we are going to slowly whittle all of this down to something that will end up being really quite reasonable. First, let's tidy up our notation a little bit, starting with our update equations for angular velocity and linear velocity. And we're going to do this by reintroducing our generalized velocity vector q dot. Remember that q dot for a rigid body system is just the stacked vector of angular velocity and linear velocity at the center of mass. We can compress this whole velocity update to the following simple form by introducing a block diagonal mass matrix and a stacked force vector, which includes linear external forces, external torques, and our quadratic velocity vector. This will clean up our dynamics equations a bit, but we still have the issue of connecting the dynamics equations to our contact constraints. Fortunately, we can use the fact that contact response is modulated by forces applied on the two objects involved in the collision. Up to this point, we've been talking about the contact forces as being applied at the contact point, which is a point in the world space. Luckily, we have a way to convert such forces to torques and linear forces acting on our rigid bodies. And that is by using the transpose of the rigid body Jacobian, here denoted by capital J. If we multiply our contact force by the rigid body Jacobian transpose, we get a corresponding contact torque and linear force. We go through this procedure in more detail in video 7, so take a look if this is a little confusing. But for completeness' sake, here is the formula for the rigid body Jacobian, which requires that all we know is the current rotation of our rigid body. And since that's information we track during simulation, this is fairly easy to compute. Now we can use this Jacobian transpose technique to apply our contact forces. From our constraint equations, we know that our contact forces are given by a scalar value alpha times the positive or negative contact normal. Thus, we can compute the total force due to contact acting on an object by multiplying each contact force by the Jacobian transpose and then summing them up. Here, n hat takes care of choosing the appropriate sign for the contact normal, and it depends on which object in the collision pair we are looking at. N sub c is the number of contacts acting on this object, and for the pairwise case, it is equal to 1. All of this gives us a new forcing term in our dynamics equations, which relates the effect of contact to the velocity of our rigid body. Conveniently, that means we no longer need to worry about the force constraint equations as we've rolled them into our dynamics equations. And having done all that, we arrive at the following discrete update equations of motion, which are already looking a lot better than they did a few minutes ago. However, we still haven't sorted out how to relate our velocity and position updates to the rest of our constraints. So let's do that next. Really, what we want to know is how to discretize our constraint equations. As an initial attempt, we can express our distance and complementarity constraints using the updated position of our contact point on our rigid bodies. This is a totally valid way to connect these equations. Doing this simply specifies that we want all these constraints satisfied at the end of our simulation time step. That's a good idea, but it makes our constraints nonlinear equations, and that makes us sad. Remember that y sub a at t plus 1 and y sub b at t plus 1 are just single points in space. This means that we can approximate these updated positions using a simple first-order velocity update. Substituting such an update rule into our distance equations looks like this. On the surface, this doesn't make anything any better. However, because delta t is typically quite small, we can replace our nonlinear equations with a version linearized around the current contact point. How do we do that? Well, let's have a look. To start, we need to zoom in on a very small patch around our contact point. Here, we've zoomed in to such an extent that we can approximate the surface around our contact point as being linear. Currently, at our contact point, the distance between object A and object B is 0, and the question we want to ask is how does this distance change if we move object A and object B very slightly? Let's start by moving object A and seeing what happens. Here we've moved object A so that our contact point on object A, y sub A, is at the new position y sub A at t plus delta t, y dot sub A at t plus 1. Now we want to find the distance from this new point to the nearest point on object B. And we can do this by projecting our displacement onto the outward-facing surface normal of object B, which is negative n. All this gives us a straightforward formula which computes this change in distance as a function of surface normal, time, and contact point velocity. Next, we can ask ourselves how the distance changes if we move just object B. And applying the same procedure gives us a similar estimate in terms of surface normal, time, and contact point velocity. The final thing we need to know is how much the distance changes if we move both objects simultaneously. And this is just the sum of the change in distance due to moving object A and the change in distance due to moving object B. Returning back to our nonlinear equations, we can now simplify even further by substituting our linear approximation for the distance function into our current nonlinear contact constraints. This gives us a set of linear constraints in terms of contact point velocity. Given these linear update equations and linear constraints, we now need to work out how to solve this problem, but not just for a single contact, for many contacts. And in order to finally close the loop on this whole discussion, we are going to need to upgrade our example case one more time, which means more circles. So here we have a great many circles all stacked up on top of one another. Using everything we've seen so far, we will be able to solve this contact problem. And as is becoming routine, the first step in the process of solving this problem is just to detect all our collisions. And we are going to store all these collisions in a list. We will always assume collisions occur between two objects, and more complicated interactions will be made up of numerous pairwise contacts. For each pairwise contact, we store which object is object A, which object is object B. We'll store the contact normal, pointing from object A towards object B, and the position in world space of the contact point. And now we are going to solve this contact problem on this arbitrary stack of rigid bodies. However, doing this all at once can be a bit tricky, so we are going to make our lives easier by solving the problem iteratively. In other words, we are going to solve our contact resolution problem by looking at one contact at a time. For each contact, we only need to think about the dynamics of two objects, A and B, involved in the collision, and the contact constraints for that ith contact. To do this, we are going to need to make some modifications to our dynamics equations. Now, warning, lots of linear algebra to follow, so if you are feeling a bit sleepy, perhaps time for a small nap before you continue. We start with the contact-aware dynamics equation for object A, and remember that this is object A for our ith contact. And to make things a bit more concise, we will condense our Jacobian transpose multiplied by the contact normal into the 6 vector G sub J A. Note that this vector is different for every contact in the object, as both J and n hat can change on a per contact basis. And now we can split this summation into the contact force applied by the ith contact and a summation over all other contacts. And finally, we introduce the term F sub IA to save me from having to type many summation symbols. Again, pay attention that for each contact we visit, indexed by I, we must compute a new F sub IA. After all that work, we've made our velocity equation look very manageable. In fact, we can now solve for the updated angular and linear velocities of our rigid body A. If we do this, we see we get a very useful result. The velocity in response to contact can be divided into the unconstrained velocity of the rigid body, the velocity we would get if simulating in the absence of any contact whatsoever, and the change in velocity due to our contact forces. And we can perform a similar derivation for our second rigid body B. So now we can replace our original discrete update equations with our new velocity updates. And that gives us the following. The final piece of the puzzle is that we need a way to insert the velocity update equations for objects A and B into our constraints. That's going to be remarkably straightforward, especially once we recall that the world space velocity on any point of a rigid body is given by the rigid body Jacobian multiplied by the generalized coordinates. Because we can invert the rigid body mapping, we can always compute the reference space point x bar from any associated world space point, including our contact points. This means that given a contact point in space, we can always compute the velocity at that contact point as a function of the rigid body generalized coordinates. Now, making that substitution will let us express our constraints as a function of our generalized velocities q dot. Okay, this is already looking much better, but the final piece of the puzzle is to express the constraints for our ith contact strictly in terms of alpha sub I, which is the contact force magnitude at that contact. The key term in both constraints is our linearized distance measure. First, we note that we can simplify this equation by introducing our g vectors, which are equal to the Jacobian transpose times the signed contact normal at the ith contact point. Direct substitution into this equation yields the following horrific output. However, we can collect all these terms, multiplying alpha I into delta sub I, and the remainder into gamma sub I, and now what appears is a very compact linear equation for the distance in terms of alpha sub I. And just a reminder that all the terms here are scalars, so this is a scalar equation. And now we can replace this system of contact constraints with this equivalence set, which is expressed entirely in terms of alpha sub I, the magnitude of the current contact we are examining. Better still, we no longer need these update equations because we folded them into delta sub I and gamma sub I, our new variables. All that remains is to find a value of alpha sub I that satisfies our constraints. And this is equivalent to solving a single point contact problem for the ith contact. So how do we solve this single point contact problem? On the face of it, these look like tricky constraints to satisfy, even though they are linear. Well, let's just take a guess. Let's start by assuming that delta sub I times alpha sub I plus gamma sub I is equal to 0. If this is true, then alpha sub I is allowed to be a non-zero value, and that's due to our complementarity constraint. So using this assumption, we can solve for alpha. But there's a problem. This alpha might be negative, which is not allowed. And that means we need to check if our constraint on alpha is satisfied. If it is, then this alpha is a solution to our contact problem, and we're done. If it isn't, we can correct our alpha by setting it equal to 0. Now, because alpha is 0, delta sub I times alpha sub I plus gamma sub I can be anything, and so complementarity is satisfied. However, we have no idea if our interpenetration constraint is also satisfied. So the final piece of the puzzle we need is to sort out if this is true or not. What's really amazing about this whole thing is that it turns out to be trivially true in this case. Let's say we solve for alpha sub I and it's negative. That means that gamma sub I has to be greater than 0, which we can see from our inequality equation. That means that if we set alpha sub I equal to 0, our inequality constraint just becomes gamma sub I, which is greater than 0, and therefore satisfies the interpenetration constraint. So no question about it, this algorithm solves the contact problem. And what's even more exciting is that just like our cloth collision algorithm, this somewhat involved flowchart can be expressed very compactly as the following mathematical equation, which computes alpha sub I and clamps it to 0 if it's negative. And that's that. That's the solution to the single point contact problem. Now we just need to extend this to our multi-point contact stack of circles. And, as I've been teasing the entire time, we are going to do this using an iterative solution procedure. To start, we are going to do a bit of setup, which involves computing our unconstrained velocities for every rigid body in our scene. Remember, we need these to build our contact constraints. Next, we are going to need a place to store all our contact force magnitudes, our alphas. So we'll build a big vector of alphas, and then set it equal to 0. Because this is going to be an iterative algorithm, we'll need an iteration counter and an outer loop, which operates until we run out of iterations or satisfy all the contact constraints. In each iteration of this algorithm, we will loop over all our contact points, and at each contact point, we use our current value of alpha to compute delta I and gamma I. We've already seen how to do that on the previous slides. We can then solve for the new value of alpha I, and we store this in our big alpha vector. Importantly, this is an in-place update, so all the contacts that we visit after this have the benefit of using this new alpha value to solve their individual contact problems. Once our algorithm terminates, we can compute our final rigid body velocities and positions. Now, this algorithm is actually very famous, and it forms the heart of a great many rigid body simulators in computer graphics and mechanical engineering. It has a very fancy name. It's called projected Gauss-Seidel. It's related to the standard Gauss-Seidel algorithm for solving linear systems. And the projection mentioned in the title is the max operation, which is used to project values of alpha onto the set of positive real numbers. Once coded up and paired with a reasonable collision detector, projected Gauss-Seidel can be used to simulate rigid body contact very quickly, and here's a simple example. And so with that, we reach the end of our discussion on rigid bodies. But more so, we actually reach the end of our discussions on solid objects entirely, as the next video in this series will provide an overview of arguably the single biggest success of physics-based animation, and that's fluid simulation. So if you're interested in learning how to generate these sorts of splashy animations using a computer, I'll see you back here next time. And as always, thanks for watching.